Hello. We didn't mean to see that video on loop, so apologies for that. Hello, welcome to this episode of Winder.AI Presents. And today I'd like to talk about a project quite close to my heart. That's all about ReFrame, a process for finding and executing RL projects. So if you haven't seen one of these before, then the first thing I'd like to do is just thank you for joining. And also, if you have any questions during this, then use the chat window in whatever whatever software whatever platform you're using. Just use the chat window to send some chat messages, and I should see them towards the end. I'll have a moment at the end to answer any questions live if I can. If you have any more questions, then you can find contact details anywhere, Winder.AI. So I was working on a project recently for a client, and I was trying to help them discover and find some new reinforcement learning approaches to some of the problems they were having within their business. And one of the people came back and they asked a really good question. What makes a good RL problem? What problems are best suited to being solved by reinforcement learning? And I think that actually this is a really tricky question to answer on the spot. I kind of did a big brain dump, and it's like, well, there should be this, and there should be not that, and there should be this, and there should be not that. But I've gone away and I've tried to sort of frame my thoughts a little bit and present it in this presentation here. It's the first time I've presented this, so if you've got any comments or questions, then yeah, feel free to reach out, and I'll add that to the presentation, and it'll be even better next time. So yeah, thanks for bearing with me. Okay, so let's get started. So the first thing I want to do is to have a quick recap of what reinforcement learning is. And the reason why I do this is because there might be some people watching that are not necessarily experts in RL, or maybe they're not even aware of what RL is. So let me just try and give a really quick recap if I can. You can also go to our website, Winder.AI, and there's loads of other talks that I've done in the past which kind of delve more into the what is RL and what are our RL applications and things like that. So do check that out if you're interested. So I'm just going to hide my face for a moment so you can see this slide. So reinforcement learning is all about the sequential decision-making process. So you see this picture at the bottom left of the slide here. We've got this loop. Reinforcement learning is based upon an idea called a Markov decision process. And to be a Markov decision process, transitions between two entities, which are the environment, which is like the real world, for example, and the agent, which could be a person, or it could be a set of rules, or it could be an algorithm, it could be anything. The interface between those two things has to be Markovian, in the sense that all of the information that's required to observe that environment is included in that update. It doesn't rely on anything in the past. It's independent of all past observations. There's obvious sort of exceptions to that idea, but it's all based, all of RL is based upon the idea of having a Markovian process and having decisions within that process that then affect the environment and the future trajectory of the agent as well. So a Markov decision process basically consists of these two entities, an environment and an agent. An agent will pick an action to perform within that environment. And then the environment will change. The action will affect that environment. And then the environment will then present a new observation back to the agent saying, you know, the environment has changed. You're now looking in a different direction. Maybe there's some new sensor metrics, some new sensor values that are being fed back, etc., etc. And also the environment feeds back this reward, and the reward signal is the thing that the agent uses to guide itself towards better strategies. So basically you reward good behaviors, you reward good actions in good states, and you penalize bad actions in bad states. And so there's a lot of technical terms I've just used there. If you're not familiar with them, then that's fine. Don't worry about it. But what I want you to take away is this idea of this continuous loop. It's sequential, it's ongoing, potentially, and it's not just a single action. Because if it was just a single action in a single step to make a single decision, then that would just be a machine learning problem. And that's what this image at the top left is supposed to represent. So reinforcement learning is not is not the same as doing pure machine learning, because in pure machine learning we typically expect to have a big offline data set. We expect to optimize for a single decision over a single step. There's no long-term rewards and there's no sequential decision making. It doesn't matter what the ML agent decides on one step, it will not affect subsequent steps. Okay, so fundamental difference, and that's really the difference that pushes a problem towards machine learning or towards reinforcement learning. Just as one example, one of my favorite examples of reinforcement learning is a video here from Winder.AI, and they have developed a robot that trained itself via reinforcement learning to pick and place objects. This is in a packing plant. You're picking it out of one box, putting it in another. Sounds fairly simple, but actually when you consider the sheer number of shapes and sizes and textures and feels and types of packaging, then actually it's a really tricky problem. And it's probably impossible to hand code all the steps necessary to pick up all types of packages, because one that would work for like a box wouldn't work for something with a bag, or one that worked for like a fabric wouldn't work for something that was made out of metal, or for example. So using reinforcement learning, though, through trial and error, through the process of trying something and failing and being punished for it, or trying and succeeding, i.e. it's in the right box, in the right place, then it can learn strategies over time that can cope and deal with all these discrepancies. So it's really good, and robotics in general actually is a really good example of reinforcement learning. Okay, so what is an RL problem in a nutshell? So these are like if I was trying to reduce down an RL problem into a few bullet points, then this is it. And our RL problems are always sequential. They are iterative in nature. People often talk about the idea of an episode, where it's either a preset number of steps or a length of time or something like that, where it's iterating for a certain amount of time and then it gets reset. That's a common pattern. Another common pattern is it never gets reset and it just continues forever, like PID controllers, for example. That's a good example of that. But the whole goal is that the actions that are made by the agent then affect what happens in the future. So if you imagine this is a robot and it's navigating a maze, the decision to go left or right at the start of that maze really impacts where you end up at the end. So a machine learning solution wouldn't be appropriate for that kind of problem. RL problems are also strategic. So all of the actions that the agent makes, you can think of them as like course corrections. You're not trying to solve the whole problem in one step. Instead, you're trying to nudge the agent towards an optimal path. And ideally, it stays on that optimal path at all times. So like maybe the shortest route to the goal, or maybe the most profitable set of actions that results to the most profit in the long term, things like that. But quite often they don't. Quite often you get situations where the agent has kind of fallen off the optimal path, and it needs strategies to be able to learn how to get back on the right path. RL problems are always defined, or good RL problems are usually defined by some sort of long-term reward. So what a reward here is, it comes back to the reward fed back to the agent. So it could be a positive one or a negative one, but either way, good RL problems, or at least problems that are really hard to solve with other technologies, are the ones with long-term rewards. So if you're trying to optimize for the long-term retention or long-term profit or anything like that, then RL is a really good solution to that problem. The actions that the agent chooses, they affect the future. They affect the environment, and they also affect the paths that might be taken in the future. And therefore, the actions also affect the reward. If the agent can't make decisions that affects the reward, then there's no, it might not even be solvable. The whole idea is that the agent is trying to navigate, is trying to create this trajectory of decisions through some complicated state space to reach an optimal reward. If you can't do that, then it's not an RL problem. So when okay, so that's like some sort of general rules of thumb of what good RL problems look like, and we'll sort of dig into them in a little bit more detail in a minute. But if you're wandering around your business tomorrow and you're looking for RL problems, what should you look for? Well, the first thing you should be looking for is the agent. Look for an entity that is performing an action, and that is quite often a person, but it might also be a pre-existing system, like a process control system. It could be a controller. It could be like a PID controller. Anybody or anything that is making decisions on a repeated basis is a potential RL problem waiting to be solved. Next, look for an environment. So when that entity makes that decision, what does it affect? What is the environment? Ideally, it wants to be as well bounded as possible, because as soon as you start working in like the real world or something, and it can't be scoped down, then that makes the problem harder. Ideally, you want a really nice, tightly bound context to work within, and that might take the form of the environment is basically only these couple of sensors that are monitoring this process. It could be an image or a video of real life, potentially. All of these are kind of like constrained versions of the real environment. Look for a clean interface between the entity and the environment. So what I mean by that is that to be successful in your RL project, you need to be able to access the things. You need to be able to access the environment. You need to be able to make those decisions in a simple way. It could be as simple as like an API. Maybe it's already got an API. It could be a physical interface like a lever or a button or a valve, for example. But there needs to be some interface that you or the agent has access to. When looking at that action, consider how an action actually affects the state of the environment. If it does not affect the state of the environment, then again, that's an indication that it might not be an RL problem. It should affect the environment in some way, in some measurable way, and also obviously affect the trajectory, the future trajectory, and the future reward. When you're looking for the actions, oh yeah, sorry, I put these in the wrong order. I should put those the other way around. When you are looking at the actions that an entity or an agent is performing, look for things like rules of thumb or gut feeling or experience. So basically, if it's a person, ask that person how they made that decision, why they made that decision. And they'll say that, well, when it's this, do that, when it's that, do this. And that's kind of like a rules of thumb that they've developed. Gut feeling is the same sort of thing, but it's less expressible, so maybe more complex. Experience, the word experience is used quite a lot. And these are all sort of indications of people having a mental model to perform an action given a situation. It's basically a strategy. And therefore, if you can articulate what that might be, not only does that give you a really good indication of the fact that there may be optimal strategies. It may also give you a bit of an indication of what to try, like what algorithms to try and what routes to try. So definitely speak to the domain experts. And finally, you're looking for some kind of success or failure. You need something in the business that is basically a KPI for the process that you're looking at. And that often comes in, it's often profit. It's just, raw profit. It could be some slightly more abstract KPI. It could be like an optimal level or an optimal temperature or an optimal something like that, where it's got to stay within these bounds. It could be something like likes or page views or anything like that. But either way, these are all forms of feedback that we can feed back to the agent to tell it that it's doing well or it's doing poorly. But what if? So this slide is talking about the situations that can arise when you don't have some of those in place. And when I get asked to do RL consultancy, it's quite often for the reason that they expect it to work, they expect strategies to form, but something's not working. It's not learning, or it's not generating good actions. It's not generating good strategies. And the reason is usually one of these. So if you only have an episode that is one step and you have labeled data, then it's clearly not reinforcement learning. It's supervised machine learning. If you're optimizing for one single decision, for one single step, and you have the data already, then it's just an ML problem. Use ML tools and solutions to solve that problem. They're much easier to use than reinforcement learning. If the episode is still one step, but there is no data, i.e. it's like a live experiment that you need to, you need to explore and you need to test upon in real time online, then that is a very rudimentary single decision, but it's still a Markov chain. It's just a single step Markov chain. And those types of problems are really well solved by multi-arm bandits and the like. And this is where you start to get into some of the RL-like challenges between exploring new options versus exploiting what you already know. And multi-arm bandits are a mathematically provable way of solving that problem. So yeah, again, one step, no data, then it's a multi-arm bandit problem. If you cannot affect the environment, if the actions that the agent makes do not affect the environment and it's fully observable. So what do I mean by that? So yeah, I've already explained what it means to not affect the environment when you make an action. But fully observable means that the entire state of the environment is completely exposed to the agent. So I'm talking about every possible parameter that makes up that environment is fully observable. If it is, then it's a classic Markov chain. So it doesn't matter what action you take, the environment does not change, it's static. So effectively, you can just keep probing and keep looking at all of the potential trajectories and effectively map out the state transitions, map out the transitions that could be made inside that environment. And once you know all of those transition probabilities, then you can just take advantage of those directly. So Monte Carlo-like techniques, sampling techniques for basically trying to sample this probability space, that's what you'd use there. And then finally, one of the sort of the most complicated but non-RL like problem is when you can't affect the environment again. So the environment is static and stationary, but it's not fully observable. So this is quite common in many situations actually. So it's a bit like a good example of this is the stock market. So it doesn't really matter what your agent does, unless in most cases it doesn't matter what your agent does. You could buy or sell anything you want. It probably won't affect the environment. It won't affect the market. It won't make any changes at all. But you can't fully observe everything. You can't fully observe the sentiment or the perceptions or the movements of prices and so on and so forth. So it's not fully observable. In those cases, hidden Markov models are really useful. So that's basically where you're trying to map out all of the transition probabilities for all of the different states that it could be in. But there's lots of hidden states that you can't see. So HMMs have some pretty cool techniques to try and find those hidden states, or at least model those hidden states. So reinforcement learning is multi-step, long-term. It includes rewards, long-term rewards, and also long-term in terms of multiple steps to make a long chain. The agent affects the environment with its actions, and it affects the outcome. All right, so assuming that you've found a problem within your business that maps quite well to some of these ideas, you've got a clear idea of what the agent is or what it could be, what the environment is, the actions are, so on and so forth, then how do you turn that into a practical RL solution? How do you come up with an RL solution? Well, when we do it, it kind of follows this process. I should have drawn a little picture with a circle on, really. We initially start with some amount of environment engineering. We actually don't touch the agents until, for quite a long time. And the reason why we do this is we recommend doing this as well, is because one, it helps you understand the environment. And if you can understand it, then you can help you can make design decisions to make it easier for the agent to also understand it. And also there's a lot of work here on simulations, and I'll talk about that in just a second. Once we've got the environment in place, then there's a lot of engineering surrounding the agent. So it's the engineering surrounding the state and the observation, engineering around the thing that's called a policy, which is basically the strategy, the model that is defining the strategy of the agent, and then a lot of engineering around the reward. And this they're all very much tied together, so they kind of developed in tandem. And then once we have a reasonable, something that we're happy with, then it comes down to deployment, and deployment is a beast in itself. Involves topics like machine learning and MLOps. And then finally we repeat. We go around this circle many times, which as a consultant is often a bit tricky because, you can't really sell this is the way, you can't sell this is the way. You have to iterate towards a solution with the client. And that can make it tricky, but usually, the people we work with understand that. Okay, so let's dig into the environment engineering section for a second because it is really important. The best first thing that you can do is attempt to build a simulation. And the reason for that is that it not only forces you to do like a data analysis, like an exploratory data analysis, like you would with any data science project. It helps you understand the environment, helps you understand the domain, helps you understand potential solutions to that problem. It also allows you to kind of quickly find potential issues with using RL as a solution. Quite often, you'll see that you're trying to create this environment, but it kind of doesn't work how you expect. It doesn't work properly, and it could be an indication that it's not an RL problem. It's also really useful to use like a random agent or just a ridiculously simple agent just to explore that environment and see what happens to the environment when something makes actions within it. And it's a really good first step to make from from a project perspective because it's progress, right? So where do these simulations and environments come from? So most of the time we attempt to simulate it, and by that we either mean that there is a simple physical process that we can model, or we can build a data-driven model. Basically, we can learn a simulation from some data. You can use generative methods, which is kind of another way of learning a simulation from a model, or you could use real life. So in real life, obviously, if you've got a situation where it is easy to get access to real life, like in the web domain, for example, if it's just a case of like segmenting some traffic off and just funneling them down this real life environment, then that's all well and good. But in many, probably, I don't know, maybe 80% of all of the problems that I work on, it's quite hard to get to do stuff in real life. So we do rely on simulations a lot. So after we've got the environment and after we've got a random agent that we think is reasonable, then we start looking at the observation of the state. So can we observe the raw state of the environment? Usually not. It's usually a representation of the state. It's like a camera or a sensor or something like that. But please note that the state and observation engineering is not feature engineering. You're not trying to make it easier for the agent to make decisions. What you're trying to do in this step is you're trying to ensure that the agent has a good observation of the state. So effectively, you're trying to add features that better represent the state of the system, the state of the environment, which may include feature engineering, but it's not kind of feature engineering in the machine learning sense. It's also not policy engineering. We're not attempting to, alter the strategy or define the strategy or define the algorithms for the strategy here. We're trying to make, a better representation of the state. Domain expertise is really important here because you kind of need to know what the state is. You need to understand the environment in order to curate and create a representation of that state. And so how do we do that? Well, I wouldn't say it's that common, but it's probably the best, is that sometimes it's possible to learn a model from laboratory conditions that convert an observation of the state into the state. So basically what you do is like, you have a real life version of that system that's under test. You have your observation, and then you perform experiments to find out what the transformation function is from the state to the observation, and then you can kind of like invert that. You just invert that, and then you're left with the real state, which is great. Doesn't happen very often though. You can apply constraints, smaller state spaces and smaller action spaces, basically trying to reduce the complexity of the environment really helps because it makes it easier to learn, it makes it faster to learn. Again, dimensionality reduction. So quite often the observation is not a perfect representation of the state, obviously, it's why it's called not an observation, but quite often it includes a large amount of information that is not useful. So dimensionality reduction techniques can help there, but you've got to be really careful actually, because you don't know at this stage what parts of the observation or what parts of the state that the policy or the agent is really going to be interested in. So you, through that dimensionality reduction process, you might be accidentally throwing away some really useful information. So I'd kind of be a little bit wary about doing that in isolation. And finally, experimentation, of course, lots of trial and error, lots of bugs. Eventually, if you've got something to aim for, if you've got something to compare against, you can usually debug it okay and sort of iterate towards a good solution. Policy engineering. So we just talked about like this box here. If you look at the picture, I'm not sure if you can see my mouse actually. If you look at the picture, the box on the left-hand side, that is what we've just been talking about. Now we're going to be talking about the conversion from that into the policy, and the policy is effectively the model that represents the strategy. They both need converting. The observations need converting to be compatible with the policy model of choice, and the actions need converting as well. So a great example of this is like, if you're using a neural network based model, then you'll need to do some transformation to get it into a format that makes it easier for the neural network to work, in between plus and minus 1, mean of 0, standard deviation of 1. I mean, things like that, things you'd normally do for your machine learning algorithms as well. You can also do a lot of like truncation and simplification at this step as well. Quite often, if you've got an observation that is a continuous variable, then it often makes sense to convert that into some kind of binary representation. You could do some binning, for example. You could do some thresholding. There's a simple version of that. You could do some classification on it potentially. If you could do some hashing if you've got really long strings, things like that, so on and so forth. Basically, you're trying to reduce the complexity of that incoming signal to make it easier for the model to learn. And then finally, on the action side, we've got another layer that we need to go through. We need to convert our policy into a valid action, and again, that could be through something as common as like a softmax function to attempt to pick one single binary, selection. It could be a continuous variable. It could be sampling from a probability distribution. There's lots and lots of different transformations that go here, and it basically depends on the interface. It depends on the interface to the environment that will expect actions in a particular format. The one thing that we haven't mentioned is the mountain range at the bottom. RL problems, because the agent affects the environment and it affects the future state of the environment, you need to explore. You can't just sort of randomly just pummel away at the same solution. You need some way of exploring states that you haven't observed before. So again, there's a lot of diversity in implementation here. I won't attempt to go over some of the more advanced stuff because I'm just running out of time. Actually, I will mention this image though. The image at the bottom left is a really cool experiment which is demonstrating is demonstrating an idea called surprise or information gain. Basically, this method of exploration, it provides a bonus to the agent if it finds new states. But what happened in this particular case was that somebody created a maze, which is great, but in that maze they placed a TV. And what happened was the agent kind of just ran towards the TV every time and got stuck because the TV was constantly showing new images. So it was always surprised at that observation, and therefore it got rewarded. I think that's a really cool, sort of real life problem as well. Reward engineering is particularly tricky because it sounds deceptively simple. You're just trying to provide a reward, ideally in a format that the business expects. And you're trying to lead the agent towards optimal solutions, but they're really hard in practice because quite often rewards, the agent finds tricks that it can take advantage of to extract value from that reward, but it's not really doing what you want. This image at the bottom is an example of that. The reward is basically to get to that square at the top right hand corner there. And the little blue box is the agent. And what it's supposed to do is supposed to pull that white box towards the wall and then jump over the wall, which it can do. There are other videos showing it doing that. But instead, what it managed to do is just like, if you look at the second frame, it kind of sneaks around the corner. It finds a little ledge that it can hang on to and just sneaks around the corner and goes to the exit instead. So, despite your best efforts, it's quite hard to get a good reward function. And we'll come back to this as a challenge actually in a future talk. Yeah, I think I'll skip that for now. So my 30 minutes is up. It took a bit longer to go through than I thought. So in summary, what I'm trying to get across here is sort of a basic picture of what an RL problem looks like and what you should look for to find an RL problem. How you solve that problem is the topic for another discussion. So I just want to recap what we're looking for. Again, it's multi-step, sequential, long-term actions, and over that you get long-term rewards potentially. And the agent affects the environment and the agent affects the outcome. So that I didn't say that very well, so let me say that again. It should be multi-step, it should be sequential. There should be long-term rewards. The agent affects the environment and the agent affects the outcome as well. If you have all of those in place, then it's probably a pretty good RL. It's probably quite well suited to reinforcement learning. Simulations are incredibly useful, just from a practical perspective, so don't throw them out just because you don't need one. They're still really, really useful for development. They don't have to be complex. They can be very simple. There is a lot of engineering still to be done. There is a lot of engineering still to be done. A lot of feature engineering, a lot of data munging, a lot of working with the raw data to try and make it look better. And rewards are hard. So the next time, I'm going to do another presentation next month where I'm going to talk about some of the challenges really when doing some of those steps. And so I recommend that you watch that next month. I think for now I'll just put my contact details up. If you've got any specific questions you'd like to talk to me about, then feel free to reach out at phil@Winder.AI. You can go to the Winder.AI website where there's lots more talks about reinforcement learning. It might answer some of your questions about reinforcement learning if you have any. And the events page is where I kind of put upcoming events that we've planned to do. But I'm not very good at doing that in advance. So there's usually only one or two up there for the next one or two things that I'm going to talk about. Okay, I'm going to take a quick look at some of the questions now and pick a couple. So we've got first question is about sample efficiency of reinforcement learning. So this is quite a tricky algorithmic concern, not strictly relevant to this presentation, but just to touch on it. Sample efficiency is the idea of an experiences within an environment. So if it is sample efficient, it doesn't need many experiences to learn an effective model. Some algorithms have better performance than others. Some algorithms are suited towards some scenarios better than others, but that's a really deep and technical topic that I can't go into at this stage. Good question though. Does there need to be a reward at the end for success? So the reward is limited to each decision. So I'll talk about this in the sort of the challenges presentation in next month. Basically, what you're aiming for is that although you typically are optimizing for a long-term reward, i.e., like, you know, total long-term multi-year profit for a customer or something like that, it's often quite hard to get the agent to learn an optimal strategy quickly because those rewards are so delayed. They're so far into the future. So quite often what you'll see in the reward engineering step is you start to see people adding like proxy rewards that are fed back to the agent quicker than the final long-term reward at the end. So basically, it is a good idea to try and guide the agent towards the optimal strategy at an earlier moment if you can. Ideally, in the best scenario, after every single action. Quite often that's can be tricky to do, but not impossible. Depends on the problem. If you're interested in real-world examples or use cases, then check out our website. We've got loads of use cases from some of the projects I've been working on. If you check out my book's website as well, I haven't actually mentioned my book yet. Oh, how rubbish am I? I'm the author of O'Reilly's Reinforcement Learning. If you're interested in learning the gory details of reinforcement learning, then go to rl-book.com. You can go to the Winder.AI website. There's a link on there, and you can learn all about it there. In terms of real-world examples, you can go to the RL Book website, and there's a big section on all of the publicized real-life examples. Go there. Yep, the slides will be available shortly. Is picking a random decision given certain situations. Is picking a random decision given certain situations a way for an agent to explore new... Yes, exactly. Yeah, so one of the simplest exploration techniques is to select a random action in a state for some proportion of the time. Yeah, it's called epsilon greedy exploration. And yeah, that's exactly how many exploration methods work. And I actually suggest you start off with that. You only pick a more complicated exploration strategy when you need it, because they tend to be sort of focused on specific domains. Okay, all right. And the last one was a comment from GOT. Thank you very much. Very kind. Yeah, I'll put all of this this video and some content on the website. I'll also put the slides on there so you can see that. And I hope to see you next month, because I'm going to be talking about some ways of solving some of the challenges, or at least I'm going to discuss what the challenges are and some ways of solving it. I kind of skipped over a few slides there. I'll include those details next time. Appreciate your time. Thanks a lot. Bye-bye.